This electrodynamics video would deal with work integrals over electric fields. I'll now begin by formulating an expression for the scalar vector potential, and alongside it, the corresponding electric field, which will differ slightly by a factor of r squared and the unit vector r. I can now consider the force that an observer would exert on some particle q, which will be negative q times the electric field. If I integrate over that, I arrive at this line integral, which will give me the work. I can then substitute negative QE into this expression, replacing F. I can then evaluate this line integral involving the electric field, and what I have is negative Q times negative 1 times this difference in the potential at the value B and at the value A. The negatives cancel out to leave me with Q times this potential difference, which I'll call delta V. Now, this potential difference is simply the work over the charge, and if I consider the reference points, say r and infinity, where in the limit as r approaches infinity, v of r goes to 0, what I have is W, the work, is just the charge times the scalar potential evaluated at r, a function of r. Now, if I consider the work over, say, two particles, hence the subscript 2, I have the Coulomb constant, of course, and then I have q sub 2 times q sub 1 over lambda sub 1, 2, which denotes the distance between the two. Now, if I consider the interaction between three particles and how this third particle will act on the first two, then what I have is q1 over lambda sub 1, 3, q2 over lambda sub 1, 3, which should actually be a 2, since it's the distance between 2 and 3. Now, if I were to, say, combine all of these expressions over some arbitrary index I, this summation would lead to a large number of terms, which denotes the interaction of all these particles. I can then condense it into this summation over here. And as you can see, the second index will always be less than the first. So what I have is the first index, I equals 1, and then j always greater than I, two summations. However, I can slightly modify the second summation such that it becomes for all j not equal to I, and as a consequence, I'll then be double counting. So I won't only have q12, but also q21, and to compensate for those extra terms, I include a factor of 1/2, hence the 1/8 pi epsilon naught. Now, if I were to say break up the 1/8 into 1/2 and 1/4, I can leave out a factor of 1/2, and I can bring the 1/4 pi epsilon sub naught over into the second summation, and this you should recognize as the vector potential, or the scalar potential, for the electric field over r sub I, which leads to this expression over here. Now, for continuous distribution, that then becomes an integral, say over the charge density, a volume integral. Now, from Gauss's law over electric fields, I can slightly modify this integral and express in terms of the divergence of the electric field. Now, take note of this identity from vector calculus, in which you consider the integral over the divergence of a scalar and electric field. That'll lead to these two terms, and by divergence theorem, I get this closed surface term. Now, I can isolate what I have over here, my integrand, which is the divergence of the electric field times the scalar potential. And what I find is that that simply is the negative of the electric field times the gradient of the scalar potential plus the surface term. Now, the electric field is simply the negative gradient of the potential, which leads to this expression for the work over here, in which I replace the negative E dot del V with just an E squared. However, when I consider these two integrals, the surface term will continue to decrease, unlike the volume term. And as a consequence of me considering all of space, I will then have very large values of r. As a consequence of that, this work integral will simply reduce to this. You can easily show that this will decrease for larger values of r by doing some simple dimensional analysis. You can easily see you have your r squared over your r cubed from the contributing terms in the integrand. Now, the way I was able to formulate this expression for work was by considering relationships between the charge density, the electric field, and of course the potential, which I can model with a diagram. I have the potential, which is Coulomb constant integral over the charge density, radius, dv, and from here I can get the electric field by slightly modifying the expression, as I've already shown, of the scalar potential. R hat r squared rho v, and from here to here, of course, the charge to the scalar potential, and from the electric field I can of course get the scalar potential through this relation, dot dl, so this line integral over here. And in the middle, I can have this slightly smaller triangle where I consider the Laplacian of the vector potential. That gives me rho, or negative rho, really, over the permittivity of free space. So these arrows are indicating you taking one quantity and relating it to another. So here I'm starting out with the vector potential. It leads me to the charge density. Here I'm starting out with the charge density, and this arrow brings me to the vector potential. Now from the potential to the field, I can express the relationship as such. As I've already previously written. And the final thing I can write is the electric field is right here. The electric field to the charge density, which would just be Gauss's law for electric fields. The divergence of the field will simply yield the charge density over the permittivity free space. So this triangular diagram highlights the relationships between these three quantities that I have over here: the field, density, and the potential. This concludes the video. However, on a further note, you can write an additional expression for the work over generalized coordinates. Now, for the purpose of E and M, usually that's not the case. However, I think for fun, it'd be nice to write it. So I have lots of knots over 2 my volume integral. And since the generalized coordinates, I incorporate the negative of the metric by using this convention. Which is just the boundary, integrating over the boundary. That's not neat at all. Of the field, and then times some, unit normal vector. And then, of course, it's a dimension lower. And this concludes the video.